but the two first-order states, but more simply, it's just the resonant exchange between a state in which the atom is in the excited mode and the cavity in the vacuum, or the atom in the ground state and the atom in the excited. This reversible energy exchange is, of course, totally different from free space spontaneous emission. In free space, when an atom decays, the photon goes away at light speed. Photons have an obnoxious propensity for propagating at light speed, and the atom remains in the ground state and the photon travels to infinity. If you have a cavity, if you have mirrors, the atom emits, but the photon remains there, trapped around the atom, ready to be reabsorbed, re-emitted. This is the basis of its interaction. And of course, you can observe that only provided the oscillation is much faster than all dissipation rates, much faster than the interaction time, much faster than the atomic damping time, much faster than the cavity damping time. And in fact, we observed that in 96, back in 96. I guess some of you were not born at the time, so it's a rather... All of you were born in 96? No, come on. You are not that old. Okay. Well, never mind. Never joke. Here we record as a function of the interaction time, which you need by the velocity, but it's a detail. We observe a probability for being in the excited state at the exit of a cavity, and we do observe an oscillation. We do observe something like 4 of these oscillations. It was, once again, a long time ago, and which prove that we are indeed in the strong coupling regime. By the way, the damping that you see here is only a technical damping. It's not due to cavity damping. Obviously, cavity or atomic damping lead to a final state, which is ground state with no photons. And here we have a 1/2. It's just some blurring away of Rabi oscillations with different frequencies. What is interesting to look at is the state transformations that arise in that. So you start from E0. Imagine that you stop here midway. You're obviously in a current superposition of E0 and G1. So you create entanglement between the atom and the cavity. If you go for a full pi pulse, E0 goes to G1. If the atom was to start with in a superposition of E and G, at the end of the day, with linearity, the cavity is in a superposition of 1 and 0 with the same coefficients. In the quantum information parlance, you would call that a swap gate, in which we swap the state of the atom and the cavity. If you go for a full path swing, E0 goes to minus E0. Why is it that? Because the spin 1/2 that undergoes a 2 pi rotation goes back to with a minus sign. G1 goes to minus G1, but G0, of course, nothing happens. So you have a conditional sign on the atom that is conditioned by the size of by the presence of a photon. Yes?
Could you please comment on the error bars? How did you...
The error bars there, it's statistical.
And by the end they get much...
They get much because we need very slow atoms, and we don't have that many slow atoms. So the error bar gets wider when the interaction time increases because we have a thermal beam, and there are not many very slow atoms in a thermal beam, as shown by Zacharias in 1953. I was not born. Okay. And so this is a quantum phase gate. So you can use that to demonstrate, and we use that extensively in the 2000s to demonstrate some basic quantum information features. Yes?
In this experiment, were you having exactly 1 atom in the more specific?
Yeah.
And how did you experiment to make sure that?
How do we make sure that we have 1 atom? This is something I skipped in the presentation of the experiment because it's one of the major flaws of these experiments. When you excite with a laser beam, and we start with a laser beam to excite the Rydberg, an atomic beam, you get a Poisson statistics for the atom number. The only way to make sure that you have 1 and only 1 atom is to maintain the average number of atoms very low, say 0.1. Then the probability to have 2 at the same time is weak enough not to perturb the signals. Of course, it's okay when you send a single atom. So each time we repeat the experiment, we send a 1/10 of an atom on the average. So we are pretty sure there is only 1. The price to pay if you need an experiment with 2 atoms is that the experiment will succeed. You will effectively detect the 2 atoms 1% of the time, 3 atoms 1,000th of the time, Okay, it's clearly not scalable for quantum information purposes. More on that later. Okay, but of course this is 96 and we kept on working. Here we are very much limited. You see that the maximum interaction time we get with the slowest atom in the beam is 90 microseconds. And then we went to the cold atom experiment. And this is something that just appeared in Fizerev letters in the last issue. This is a Rabi oscillation signal with slow atoms in the cavity, where you see 20 oscillations and no damping, and with statistical error bars, which are obviously constant. And those 20 oscillations do not damp. You see a small irregularity in the amplitude, but it's fully contained in the theory, and it's just that we have a small residual thermal field in the cavity. So you have a mixing of the oscillation due to 0 photon mainly, and a little bit of oscillation due to 1 photon occurring in the square root of 2 frequencies. But you see that, well, when you see that, well, it's perhaps an overstatement, it's certainly an overstatement, you start believing in quantum physics. Okay, 20 oscillations, the atom and the cavity exchange the photon about 20 times. No, that's vacuum. Okay, it's boring because it's a sign. Okay. What happens if you have a mesoscopic field? What happens if you make the Rabi oscillation not in the vacuum, not in Phillips large fields, of outrageously large fields, but somewhere in between? Say in between 1 and many, it's 10. What happens for the Rabi oscillation in mesoscopic field? This is a simple exercise to work out. You can express the psi of t in terms of En and Gn, and what you find is those coefficients. It's a simple exercise in dressed atom picture. And at the end of the day, you get that the probability for being in the excited state is the sum over all possible n's of Rabi oscillations at the frequency omega n, or omega 0 square root of n plus 1, weighted by the probability for having n photons in the cavity field. This is just the Poisson law of current states. So this is a very simple expression, which you could guess without making the calculation, obviously. But if you plot it, you get surprises. This is what you get for 15 photons, theoretically. You see that the oscillation collapses, stops, and revives. And those revivals there have been the source of an infinite flow of ink in the reviews in the early 80s. Why is it? Why does it collapse? We can understand that very clearly. It collapses because we have many frequencies there. So rapidly, these many frequencies come out of phase. And you can compute the time it needs to collapse. It's about the period of a vacuum Rabi oscillation. This collapse would exist even if the field was a classical random variable. If you mess up the amplitude of a classical random field by adding noise to it, you will get a damping of the Rabi oscillation in a short time. But the revival, why does the oscillation come back? It comes back because here you have irrational frequencies. It's not harmonic, it's omega 0 square root of n. But you have a finite set of frequencies. And whenever you have a finite set of frequencies, if you wait long enough, they all come back into phase after some time. This time is easy to compute. You need to compute how much time you need for the oscillation corresponding to n photon and n plus 1 photon to come back into phase. And you will find that this time is independent of n, and so at this time, all oscillations come back into phase. And this time is square root of n times larger than the collapse time. Okay? So why is there a revival? Because the field amplitude is quantized. Because the Rabi frequencies are quantized. And it's why it triggered so much interest. It's a direct evidence of field quantization. And obviously, in the limit of very, very large n's, the collapse, the revival times goes to infinity, whereas the collapse time remains finite. You have a collapse, and it never revives. Why is it so much complex at later time? I will allude to that a bit later. Let's do the experiment. Obviously, we need long interaction time. We needed the slow atoms, and we needed 40 years of work, basically, to get this signal. And what do we see? This is a 13 photon coherent field. We see a collapse of the oscillation, a long idling period, and all of a sudden, well, okay, not that all of a sudden, we see a revival of Rabi oscillations. And the red line is just a numerical fit, taking into account all the known imperfections of the experiment. There are still imperfections in that experiment. So you get a collapse at very, very large time. And I think it's the longest collapse ever seen. How does it reveal the quantum nature of a field? Once again, if a collapse occurs, it's because we have a finite set of frequencies. How do you monitor that? You make the Fourier transform. So let's Fourier transform this signal. This is the Fourier transform. The Fourier transform, well, there is a noise level that is there. So below that, you say, but the Fourier transform has peaks. Where are the frequencies of these peaks? Precisely at omega naught is 50 kilohertz. I should have said it to start with. It's an important quantity. Omega naught over 2 pi is 50 kilohertz. Meaning that the period of the vacuum Rabi oscillation is 20 microseconds. You see all those frequencies here, the vertical line, correspond to omega naught square root of 10, omega naught square root of 11. You directly see here the spectrum of the field amplitude in the cavity, and you directly see that the spectrum of the field amplitude is quantized proportional to the square root of the successive integers. If you say that the field energy is the square of its amplitude, which is quite reasonable, you directly monitor that the field energy in the cavity is quantized with a photon number. It's by far not the first. There are 70, 80, 90 years of evidences of field quantization, experimental evidence, but yet it's a direct one, beautiful one. Let's try to get a bit more look into that. And in order to do that, the shear expression with the frequencies is not the ideal. We should go to a beautiful approximation that was found independently by Gia-Banaklosh and Buzek et al. In the 90s. Working out an expansion in n minus n average, where n average is the mean photon number, and neglecting higher order terms, and turning the crank for a couple of pages, you can show that any time the atom field state can be cast under this way. Psi plus, psi plus, plus psi minus, psi minus. This is atomic, this is cavity. What are psi plus and minus? Equal superpositions of E and G. So, on the equatorial plane of the Bloch sphere, with a phase that evolves like omega naught over square root of n me. A very slowly varying phase. What are psi plus and psi minus? Coherent states, derived from the initial coherent state alpha, with phases that evolve in the same way in the Fresnel plane. Let's try to represent that. I have the atomic state in the equatorial plane on the Bloch sphere, and I have a current state evolving in the Fresnel plane. Just put the planes together, pictorially. And just let's represent the fields like an amplitude and vacuum fluctuations, and the atomic dipoles as Bloch vectors. What these expressions say is that we have the plus state correlated with the plus field, the minus state corresponding to the minus field. With the proper phase reference, the atomic state plus is in phase with the field, the atomic state minus is pi out of phase with the field. And what is the further evolution? A rotation in opposite directions in the phase space. This is beautiful. What is the link with the Rabi oscillation? We start like that in the initial state. Psi A plus and psi A minus, which are dressed, do not rotate in the same way. But initially, the coherent states of the field factor out. So basically, you have a superposition of psi A plus and psi A minus that get a respective phase. And if you work out by superposing these two atomic states what is the probability to be in E, you get a Rabi oscillation. That's the Rabi oscillation. So initially, in the early stages of the separation, you get oscillations. But after some time, you see that the two cavity states become distinguishable. So basically, the initial Rabi oscillation results from an atomic interference, from a quantum interference, between the two atomic states. But after a while, the two cavity states linked, entangled with the atomic states, get distinguishable. Whenever you have a quantum interference, nothing in nature and the universe should tell you which state you are in. If you have anywhere what is called a wedge path information, the interference is lost. We are back to the early debates between Einstein and Bohr. So whenever these two states here in the cavity are separated enough, you could, in principle, access the cavity information, which will tell you whether you are in Ca plus or Ca minus. So you should not have quantum interference, even though you might not access practically this information. And so all the collapse part is in this period. You don't have interference between, you have information in the cavity about the state of the atom. Not this precise time here. The two atomic states unite. The atom factors out, disentangles from the field, and the field is left in the beautiful Schrödinger cat superpositions with large fields. What is the revival? At the end of the day, those two components merge again. The interaction, the information in the cavity about the atomic state is erased, and the atomic interference takes place again. You erase, it's a kind of quantum eraser. You erase the information stored in the cavity. Why is it that the contrast is not the same? Why is it that the width of the revival is much larger than the width of the collapse? Because in the process there are higher order terms that slightly deform the current states. This is the ideal picture. The actual states are elongated, kind of squeezed, and that makes the revival a tad longer. So it's beautiful because it's an illustration of complementarity as well. Once again, the interesting time is the time of the cat, the half time of the revival, because the cavity is left in a superposition of two states with opposite phases. Well, there is an additional quantum phase in between. So it's a very large Schrödinger cat. Can we check experimentally that we do have a cat? Yes. By stopping the interaction at this time, getting the atom out of the way, or resetting the atom, and studying the Rabi oscillation in this cat. And one proof that we have a cat is that if we look at the Rabi oscillation, there are two revivals. This is the standard quantum revival. This is an additional revival due to the fact that we are making a Rabi oscillation in a cat. And in fact, if you look at this signal and make the Fourier transform of it, you only get the odd photon numbers. And one of the properties of a cat is to have a well-defined parity. Well, there is a translation behind that. I don't want to come into the details. I refer you to this archive paper if you want more information. Okay? So it's surprisingly simple, but yet surprisingly complex, just to have the Rabi oscillation of an atom in a current field. Now I would like to switch gear and to, if there are no questions on that, I would like to switch gear and to turn to the dispersive interaction and start by speaking of an ideal QED measurement of the photon number. You know everything about ideal measurements, the ones that are taught in elementary textbooks. Most of the time, they provide discontinuous results, and this is one key difference between quantum physics and classical physics. And for instance, if you measure the energy inside a field box, a photon box, you would find something that is a multiple of h nu. This is basically what we did with Rabi oscillation. You have a quantum indeterminacy. Of course, God is playing the dice behind the scene, as Einstein used to say. And it means that the result of a measurement is most of the time random. If you have a current field in the cavity, measure the photon number, you will get photon numbers with a P of n distribution, with a Poisson distribution. And a key ingredient in the quantum measurement is repeatability. People say most often that the projection postulate of a reduction, wave packet reduction, is something that is outrageous, obnoxious, and complicated. But in fact, it's a simple requirement of reproducibility. If you measure the photon number in a cavity, if you get free, if you resume the experiment, consistency of physics says that you should get free. And that's the heart of the measurement postulate. But in fact, of course, most of the measurements you do in labs don't obey this. For instance, when counting photons, you have no superb superconducting photon detectors. I don't know if you are using them. Things that can tell in this laser pulse there are exactly 3 photons. In this laser pulse there are exactly 5 photons. Well, above 3, 5, it begins to be a bit indistinguishable, but marvelous, 100% detection efficiency, and it counts the photon number. But yet, there is one important thing that the experiment is missing. Once you have detected the photons, there are no photons. Most of quantum optics is a post-mortem science. You work with photons that are dead. And a dead photon is no photon at all. And that's embarrassing. And this is one reason why this amphitheater is tilted. Because you are not transparent. Your eyes have to absorb the light to convey a signal. And by the way, it says something very interesting, that the invisible man is blind. He cannot absorb light, so he's blind. Something that the science fiction writers never thought of. From time to time, they should learn physics. So, photodetectors are very bad, very crude detectors. They destroy the system they measure. Can we do better? And there has been a huge literature originating in Brzezinski writing in the 70s in the context of gravitational wave detection. In principle, yes, you can. Well, this is a joke that doesn't work any longer in the States. Yes, you can detect photons without absorbing them. Yes, you can think of detectors that go click when a photon goes through and yet are perfectly transparent. And it has been realized in the quantum optic domain, particularly there is a beautiful review by Philippe Grangier about that, by interacting a signal and a matter beam in a nonlinear medium, but it works only for very large fields, and it works only for correlating the quantum fluctuations of beams, and certainly doesn't work at the single photon counting level. Can we do at the single photon counting? Yes, we can. And to put that in terms of a thought experiments of the early quantum physics, the idea is the following. We have a photon box, and in the photon box we put a transparent clock. And the tick-tack of this clock depends upon the photon number by some unspecified mechanism. So you put the clock for 1 hour. If it's delayed by 1 minute, you know there is 1 photon. If it's delayed by 2 minutes, you know there are 2 photons. And since the clock is transparent, it doesn't absorb the photons, so the photons are still there. And if the next hour you resume the measurement, you will get the same result. Totally realistic, of course. How do we do it in practice? The box is the cavity, the clock is the atom. It's a good clock. An atomic clock is a good clock. So the clock is the atom. And of course, we have to go to the dispersive interaction. Rabi oscillation is a dead end. It leads to energy exchange between the atom and the field. It's not what we want. So we will go to the dispersive side and just use the light shifts that the atomic transition undergo in the cavity. I remember you that the EG transition is shifted in the cavity by an amount S naught, omega square over 4 delta, times 2n plus 1. I don't care here with the 1. I have here a 2n. So the frequency of the atom is changed. If I send in the cavity an atomic superposition E plus G, its phase will be changed by an amount phi naught, where phi is basically the product of S0 by the interaction times n plus 1/2. Just get rid of the factor 2. So I can imprint on the phase on the atom and information the photon number. If I look at that in the Bloch sphere, what will I do? Before the atoms enter the cavity, the atom is, say, in G initially, and we make a classical pi over 2 pulse that puts it in E plus G. I send the atom through the cavity. The phase of the atom changes while it crosses the cavity. When it exits the cavity, it has a different phase. How much the phase is different? Here I have plotted the case where the phase shift per photon is pi over 4. So 0 is shifted by pi over 8. 1 by pi. If there is 0 photon in the cavity, you have a shift 1 over 8 because of this term. If there is 1 photon, you add pi over 4. 2 photons, you add pi over 4. 7 photons, you are there. 8 photons, you are back on the same state. Okay, because rotations by pi over 4, you come back to the same state after a while. So you see that you have different atomic states correlated to the photon number. If you want to make an obvious experiment, the obvious answer is that these states are not orthogonal. Orthogonal state on the Bloch sphere is states on a diameter. So these states are not orthogonal. There is no way by which, with a single atom, you can distinguish orthogonal states. So let's make things simple. And let's assume that in the cavity there are only 0 and 1 photon. It's a weak field, so we know that the photon number is not larger than 1. Let's tune the phase shift to be pi exactly per photon. So 0 is pi over 2 shifted, 1 is 3 pi over 2 shifted. And now we have two states of the atom that are orthogonal. I make a second pi over 2 rotation at the exit of the cavity, so that I map the atomic state corresponding to 1 photon on the north pole, E, and I map the atomic state corresponding to 0 photon on the south pole, G. By detecting the atom, I know whether there is a photon in the cavity. But of course, I have not absorbed the photon. It's supposed to be still there. Of course, the atomic energy might have changed in the process, but this energy comes from the classical pulses that I'm putting on the atom to mix it in a superposition of E and G to start with, and to put it finally on the vertical axis. We did the experiment in 2006. The commutation is a bit long. We did the experiment in 2006. Unfortunately, I was not in the lab the night we saw that. And we had in real time of the scopes, this is the time in seconds, blue bars appearing when an atom was detected in G, and red bars when an atom was detected in E. And we just let the cavity at its base temperature of 0.8 K. Why is it? At 0.8 K, 50 gigahertz, you have 5% of a chance to have a photon at any given time. And you basically never have to. So it's a good field that is thermal field at 0.8 K is either 0 or 1 photon, one with a small probability, but it's okay. And what do we see? Many atoms coming out in G for nearly 1 second. These are seconds. It's a long macroscopic time. Many atoms come out of G. Of course, the pulses we apply in the atom, you might have recognized the Ramsey interferometer, of course. The pulses we apply in the atom are not perfect. The atomic detection is not perfect. So 1 every 10 times or 20 times, the atom is detected in the wrong state. But okay, we can make a majority vote and decide there the majority says G. And if we believe in the experiment, it says that the cavity is empty. But suddenly here, in between two detections, the regime changes. And now we detect a vast majority of the atoms in E. And if I believe in the experiment, it says there is one photon which appeared in the cavity. Which appeared from where? Created by the residual thermal fluctuations. And this photon here has stayed for 0.5 seconds. We had time enough to code it Methuselah. Just can say that in 0.5 seconds if you are well trained. It's much longer than the cavity damping time, but of course the cavity damping time is just an average of a lifetime of single photons. And then all of a sudden, we go back to G. What is important to notice here is that you have hundreds of atoms which all entered the cavity and said there is one photon in there. If you make a standard photodetection experiment, which would be simple, just going to the resonance interaction, the first atom goes out of the cavity saying, I've seen a photon. And the next says, no, there is no photon left. Of course, you have taken it for you alone. There, the photons are more sharing the photon. the atoms. They just convey the same information, and they just repeatedly say there is one photon in this cavity. And this is the clear indication that it's indeed a quantum non-demolition ideal measurement of a photon number. And so it gets back, and this is a long-lived photon. Photons have a big advantage over men, is that they don't age. When this photon had lived 0.49 seconds, it still had a complete average lifetime to go. Okay, it's just a Markov process. There is no aging, and you can see a photon living for centuries in that cavity, and it still have at any given time on the average 0.13 seconds to go, which is not the true for men, unfortunately. It seems so. Okay, so this is just random fluctuations of the thermal field. We can make another experiment which is instructive on the very, very basic things of quantum mechanics. In that experiment, we purposely prepared, through a resonant Rabi interaction, one photon in the cavity at the initial time. And we started measuring it QED way. And I don't give all the detection details, I just give the majority vote. So we send one photon in the cavity, we monitor its presence, and suddenly, poof, quantum jump. Yes, this is a quantum jump of light. It disappears because it has been absorbed, diffused. I don't know what the channel mechanisms are, but it disappears. And this one has lived kind of the average lifetime. So you see a telegraphic signal. But of course, your classical intuition of the damping of a cavity is like the damping of a swing. You expect the energy to go down exponentially with time. If you use the Lindblad equation and write down the evolution of a one-photon state, very simple exercise, you will get that it's exactly the same exponential lifetime as the classical energy. Exactly the same. So quantum mechanics predicts an exponential there. My experiment gives a stepwise function. Who is wrong? They don't want to say that my experiment is wrong. They don't dare saying that. No, no one is wrong. They both say different things. Quantum physics, density matrix, wave vector, whatever you want, whatever interpretation you want, gives you probabilities, gives you averages over very many realizations of one experiment. E plus G has a 50% chance to be in E. Okay, statistically. But nothing in the world can tell you what the result of one given quantum mechanics experiment will be. There is no way to predict when you measure an atom in E plus G whether you will get in this very experiment E or G. There is no way when you measure the decay of a photon here to tell whether it will decay at 130 milliseconds later or earlier. Quantum mechanics doesn't say anything about one realization of the experiment. But it tells you stats. So how do you reconcile? By going stats. Average 5 trajectories. You have 5 steps. And you have here a bit of thermal photon that appears. Could happen from time to time. 15 steps. This is the quantum mechanical prediction, taking into account everything. No adjustable parameters, just the temperature. 900 steps. You don't see the difference. Well, it tells you something wrong, something strong about quantum measurement and quantum physics. So if your experiment one day doesn't work, you can tell your advisor this is a unique realization of the experiment. There is a probability for failure. In fact, everything is correct. Just come back tomorrow. Okay? This is an advice. And if he takes it, is that he doesn't know quantum physics, and I urge you to change your subject. Okay? This is fun. Okay, so we know how to count from 0 to 1. Of course, computer science people will tell you it's far enough. Being physicists, we wanted to count to 7. From 0 to 7. So I remember we set the phase shift to be pi over 4. So we have 8 atomic states correlated to the photon number 0, 1, 2, 3, 4, 5, 6, 7. And that's it. And then 8 goes back. So there is no way to avoid that. Our measurement is periodic with n, and we have to be sure that the photon is within one period. If I make the second pi/2 pulse at the exit of the cavity, I can map one of those states, say 1 onto G, the other onto E. But of course, the others are in between E and G, and I cannot distinguish them. When I get the atom in E, I don't know in which state I am. But yet I know something. I know, for instance, that if I detect the atom in E, for sure, I have not one photon in the cavity, because in that case, I would for sure detect the atom in G. So I don't have full information, but I have partial information. How do you describe that? Each atom makes a generalized measurement of the cavity field. Each atom leads to an upgrade of the density field matrix that is sandwiching between measurement operators that depend whether J is E or G, and of course normalized. And what are the measurement operators? You see that. The probability to be along Z is a sign function of the number of photons. So mg and me are just complementary sign functions of the photon number. So each time I detect an atom, I have to upgrade the density matrix like that. Well, this is complicated, but of course I am only interested in the photon number distribution. So I can just write the diagonal of the density matrix, just reduce the mg and me's, which are also diagonal. And what I get is that the new photon number distribution when I have detected an atom in state G is the old photon number distribution multiplied by the probability to observe state G if I have n photons in the cavity and normalized. What do you recognize here? 1750, something like that? English clergyman? Bayes' law. It's the law of conditional probabilities. It's nothing but the standard plain classical probabilities Bayes' law. And in fact, if you think of quantum physics, many of its counterintuitive features are counterintuitive features of the Bayes' law itself, which is, I think, one of the most puzzling laws in probability. But here, what does it say? It says that the photon number distribution before is multiplied by the conditional probability to get the state I observed when the photon number is there. How do we illustrate that? Imagine that I know, first atom, I know nothing of a photon number. And I use a slightly different labeling here of a state, so it's 0, which leads to E, and E, which leads to E. Okay. So I know nothing of a photon number, so I have to assume that the photon number distribution is flat. And I multiply it by a conditional probability, which for a detection in E is a sign. It's here maximum for 4 and 0 for 0. Ideally, it's strictly 0 for 0 and 1 for 4. With reduced experimental imperfections, it's somewhere in between. So you see that if I know nothing of the field before, I still cannot point out a photon number after, but I know that it's more likely to have 4 and less likely to have 7 and 0. Just Bayes' law. If I would detect the atom in the other state, I will reduce the probability for 4 and increase the probability for the others. And obviously, if I discard the information about the atom I just have the sum of these two probabilities, which is the initial one. I did nothing. So each time we detect the atom, we multiply the photon distribution by a sign, which depends upon the atomic state we have detected. And so let's do that. This is one realization in the experiment in which we send about 100 atoms through the cavity. 110, because 110 is the speed limit on the French non-highways. Okay. Initially, I know nothing. In fact, we had a current state. We know what it was, but we don't want to know it. We know nothing. Detect the first atom, multiply by a sign. I get some probabilities a bit out of the game. Some others are reinforced. Detect second atom, multiply by another sign. Reinforce or delete the effect, I don't know. But in fact, what you see is that after a few tens of detection, you think the photon number is 4. But 5 still has a probability. 5 is still in the race. And then 5 takes over. 5 catches up on 4. And 5 crosses the winning line, yes. and at the end you have 5 photons. What you witness here, in fact, is the progressive collapse of the wave function in a quantum measurement when you add information provided by partial measurements. Of course, you say it's unwavering arguments, the product of the signs, it might never converge, it might... Denis Bernard of the Laboratoire de Physique Théorique in INS has shown with martingale mathematics that it unconditionally converges, and it doesn't converge a null measurement ensemble of trajectories. Okay, null measurement, it means that it never occurs. So it always converges for all particular. Of course, this is one realization of the experiment. If you redo the experiment, you get another photon number. Because the signs are not the same, the atoms are not detected in the same sequence. And so you get another number. At the end of the day here, you have a P of n. Here the P of n is delta 5. But what you can find is compute the average of SP of n and look at the binning of these averages of the final photon number over a very, very, very many realizations of the experiment. And this is the binning. What do you observe? In 20% of the cases, you don't get a precise photon number. Why is it that? Most probably because due to relaxation, the photon number has changed during the time, about 20 milliseconds, you need to gather these 110 atoms. But 80% of the time, you get an integer photon number, which is not at all built in the a priori signal that we are analyzing. Just multiply P of n by signs. It's not clear that it would converge. And indeed, it converged. And the weight of these photons is precisely the Poisson distribution that we know in the initial field that we have observed. So we see that the experiment gives us the right probabilities. It measures the photon number. The photon number is random. And the randomness obeys to the proper Poisson law. You would say there is a bit excess there. Yes, that's right. But what is the excess? We have a little bit of probability to be innate. And once again, 8 and 0 are indistinguishable. And if you put it this extra there, is precisely what lacks there. Well, within error bars. About 100% error bar, but never mind. Is it really QED? To know if it's QED, you repeat. And what we do, in fact, is what we did for the 0-1. We keep sending atoms for a long time. And at each time, we analyze the 110 last detections. And we decide upon an average photon number. And we plot it as a function of time. And here it is. This is the time we need to gather the first 110 atoms. So we evolve from a photon number distribution where we know nothing, but that is between 0 and 7. So we have an average initial of 3.5. And we converge, and here we converge to 7. And then here we have a plateau. And on this plateau, we detect altogether 200 atoms. So we have one measurement which says 7. The next measurement says 7. So it's QED. And then we see the photons escaping one by one out of the cavity mode until it's finally in the vacuum. I plotted this signal theoretically in 88, and we have observed it in 2008. So you need 20 years to get to that. Once again, science needs time. And basically, we needed to develop the cavity technology that is behind that. I think it's time to speak a little bit of the quantum Zeno effect. Because everybody, when we spoke of that experiment in the early symposia and conferences, said, can you try the Zeno effect? So, okay, we came back to the lab and tried. What is the Zeno effect? It's the quantum implementation that a watch kettle never boils. This works only in England. Okay, no other country thinks a watch kettle never boils, but okay. You imagine a system that is undergoing a coherent evolution, some sort, for instance, an atom that undergoes a current Rabi oscillation between two levels, and you measure frequently in which level it is. And the key point is that you get, in this case, a quantum jump in evolution between the eigenstates of the measured quantity. Obviously, You will find the atom in one level, suddenly in the other. But the switch to a level than the other is much slower than if you don't make measurements. And the more measurements you make, the more you confine the atom, the system, to its initial state. Of course, you need to make a measurement that is non-degenerate, in which the initial state is non-degenerate eigenstates of a measurement. And at the limit of infinitely many measurements, you do not evolve at all. Basically, the key point in all that, and we will illustrate that in a bit of maths in the next slide, you are in the Hilbert space, I'm the system, I'm evolving in my Hilbert space, and I'm prescribed to follow a gentle path through the Hilbert space by a current drive. But now I'm here. I start making a little step. But someone measures me. As my step has been little, I will most probably be projected back on the initial state. And since I'm projected back on the initial state, I did nothing. And I will try again and do nothing. And try again and do nothing. And if this is done frequently enough, I will never move. But perhaps suddenly, at a later time, I will be found directly. Well, this is very difficult. I could not do it faster. At the end of the evolution. I should invent teleportation. So how do you do that? It's enough. You take a quantum system in zero, which evolves with an Hamiltonian V during a time t, and you slice this time t into n slots, and you perform one measurement at the end of that slot. At the time t over n, the probability for finding the atom in its initial state is 1 minus something that is proportional to t squared over n squared. Why is it that? Because it's a current evolution, and current evolution, the probability starts always quadratic with time, plus over terms. And so the final probability for being still in zero after n measurements is the probability to find the thing in zero after one measurement to the power n. This is small, so that expands nicely in t squared over n. And you see that when n goes to infinity, the probability from departing from the initial state goes to zero all the way. The key point in that is that the evolution needs to be in t over n time interval in t squared over n squared. It should be quadratic. If it's not coherent evolution, if it's just relaxation, for instance, after a time t over n, you have a probability of departure that is t over n. That is linear with time. Exponential damping, for instance. To the power n, it means that you have no Zeno effect. So you can block a current evolution. You cannot block, for instance, spontaneous emission. There is no way of inhibiting a decay by observing the system. But there is a clear way. Well, you can inhibit what is useful. You cannot inhibit what is painful. This is a general feature of life. Yes? It has to be t squared because when this is the probability in one time interval t over n. Okay, t squared over n squared. And you have to get the final probability for staying, you have to exponentiate n. And when you make 1 minus epsilon to the n, the first time is 1 minus n epsilon. So if epsilon is the departure probability in one time interval, you have to have epsilon decaying at least as faster than 1 over n. And in fact, as n 1 over n squared. 1 over n square root of n would do if you could do it. But, okay? That's it?
Because the probability is also proportional to the time.
The probability, the total probability at the end is proportional to the square of the time interval. Okay, so let's do that. Let's do that how? Very much. It has been done already in trapped ions by Wineland in the 80s. The recognition that an ion blinks due to quantum jumps was one of the major steps in quantum physics. People didn't believe in quantum jumps just because if you make the optical block equations, you find a steady state with no jumps. And it's Cohen-Tanuji that sorted the thing out with Dalibard and others in a seminal paper where he showed that if you look at the proper quantum correlation functions, you find a scar of the quantum jumps that people were observing in the experiments. The ion was blinking. Okay, so we did that on the field. That's easy. The current evolution will be the injection of a large current state in the cavity by an external source, but an injection that is stepwise. So instead of directly going to a large field in phase space, we will go by little steps in phase space until we reach a large coherent field. And now we will add to these little steps quantum non-demolition measurements of the photon number. So here is what we got. This is the final number of photons as a function of the number of injection, of number of steps. If we don't make measurement, we observe a quadratic start because the amplitude we get at the end is proportional to the number of steps. So the final photon number is proportional to the square of the number of steps. This being said, it was not easy to see that because you need a huge phase stability of the experiment over hours. It's not that easy. And after a while, it saturates because you have to compensate. You have the losses that come into play for very large fields. If we interleave measurements, and we can calibrate how many photons we inject per step, and you see that we are measuring thousands of a photon with an uncertainty of 5%. Quite delicate experiment. If we measure, the field just doesn't go. Zeno effect. It works. You prohibit a system from evolving. We have seen them, you can look, there is in fact a small growth of a residual thermal field that can be explained theoretically very, very easy. We did other things more recently in quantum xenodynamics, but I have no time to tell that. Quantum xenodynamics has been invented by Paolo Facci and Saverio Pascasio from Bari. And the key is, what if the measurement has degenerate eigenstates? Then you see that your quantum system can wander, but it's a limited subspace of the Hilbert space. And that has... but of course, I think you would have a feeling of incompletion if I wouldn't discuss Schrödinger cats. So we'll discuss Schrödinger cats, and I will go back on the complementarity thing. Remember this drawing by Bohr, remade by me a few years ago with modern techniques. But I use the same X screws that Bohr was using in his original paper. A moving slit interferometer. It's just a conceptual thing that illustrates the wedge path problem. You have a Young slit interferometer, but one slit is mobile. It can move. And of course, if a particle goes through this slit, it gives a kick to the slit, and hence the slit starts moving. If the slit is very heavy, which is the kind of the case of most interferometers on Earth, then the motion of the slit is negligible compared to the zero-point motion, and then you have no information about the path followed by the particle, and you get beautiful Young fringes. If the slit is very light enough to have its motion changed appreciably by deflecting the particle, you can, by looking at the interferometer at the end of the experiment, decide whether the particle had gone for the upper path or the lower path, and accordingly, you have no interference fringes at all. You can put that in terms of a discussion, and it was initially in terms of a discussion of the Heisenberg uncertainty relations. You can also put that in the spirit of what we did with the Rabi oscillation, in terms of a wedge path information and entanglement. The interfering particle is entangled with the motion of a slit, and this entanglement results in a dispersion of the fringes. It's a very enlightening. I encourage you to work out this exercise in details. Well, not with this geometry. It's dirty because you have plenty of signs and angles with this geometry. But you can think of a simpler geometry. I can tell you more on that if you want. Let's do that. And let's do that, of course, not for a physical interferometer, but for a Ramsey interferometer. Once again, before the atom enters the cavity, I can apply pulses, mostly pi/2 pulses, classical ones. So, if I have just these two pulses, going from E to G, forget about the cavity in the middle, can result from either making the transition in the first Ramsey pulse or making the transition in the second Ramsey pulse. Accordingly, you have two quantum paths that lead from the same initial to the same final state. you have to sum the amplitude n squared to get the probability. And since these amplitudes have respective phases, you imagine that there is a phase shifter somewhere, you would get at the end of the day an interference fringe signal and an oscillating probability as a function of the dephasing for observing the atom in G. This is very much the heart of Ramsey interferometry, atomic clocks, whenever you want. Okay? Now let's place the cavity in between. As an observer, as a meter of the atomic state. And a meter needs a needle. Well, you are all used to digital meters. But in the very ancient times, before the computers, there were meters where you had a dial in white with a scale, with engraved digits, and you'd have a needle moving in front of the scale, telling you how large was the current, the temperature, whatever. It was very, very old times. So let's put a needle, and the needle is obviously a current state. I put a current state in the cavity, and I send the atom. What happens? Converse of the QED effect. The atom in the cavity has indeed an index of refraction. It changes the cavity frequency. While crossing the cavity, it's like in a violin, if you make the vibrato and move a little bit your finger, suddenly it makes it returns to the same note. And since you have a transient shift in frequency, you have, at the end of the day, a shift in the phase. So an atom that crosses the cavity will change the phase of the field. And as we have seen, E and G have opposite indices of refraction. Well, n minus 1s, indices minus 1. So E will make a positive shift, say, and G will make a negative shift. And so you see that quite neatly, the field in the cavity is a needle which tells you which path the atom has followed in the interferometer. It's just very much Bohr experiment, just put in actually feasible experimental terms. If you want to work out the precise phase shift, they are there. Okay, this is a simple exercise, master degree exercise in quantum optics to calculate what the shifts are. We don't care. Let's go to the basics. Where is complementarity? Imagine that the phase shift is small. If the phase shift is small, the two current states at the end of the day are nearly indistinguishable. So you have very, very little information on the path the atom has followed in the interferometer, and I expect to see beautiful fringes, Ramsey fringes. If the phase shift is large, on the contrary, the two current states left in the cavity after the interaction are fully orthogonal. Well, as orthogonal as current state can be. They are never orthogonal, but they can be orthogonal if APP. And so I have a complete information whether the atom has transited before entering the cavity or will transit after exiting the cavity, and then I expect to see no fringes. So I expect by changing this dephasing, which I can tune easily through the atom cavity detuning, I would be able to see this complementarity effect. In fact, I can. This was performed in '96, something like that. This is the Ramsey fringes we record when the cavity is in the vacuum. This is the fringes we record when we put in the cavity 9.5 photon fields, but make a huge atom field detuning so that the phase shift is very, very, very small. And this is to scale. This is amplitude-free fields. So we see fringes, they are a bit shifted. This is an effect of a light shift, obviously. They are a bit shifted, but they have a good contrast. But when we reduce the detuning, the phase shift increases, and gradually the fringes are washed out. So it's a beautiful illustration of the complementarity concept. If you get information on the path, you don't have fringes any longer. Of course, seeing that a signal disappears, I tell you that for everyday life in the lab, seeing a signal disappearing might not be the harbinger of an interesting quantum effect. You have to check in detail that it disappears in the proper way. And we have measured the contrast as a function of the angle, the contrast as a function of the photon number, to make sure that it's the effect we expect. Okay. It's very easy to make a signal disappear. The easiest thing in life. What is interesting now is that at the end of the day, when you detect the atom in E or in G, what is left in the cavity? when you detect the atom, you don't know what happened in the cavity. You have not looked yet. So what remains in the cavity is indeed a superposition of a field with two different phases. They are not opposite, phase opposite. It was an early experiment. They were just split by a 30 degrees angle. But yet it's a Schrödinger cat. So we expect in the that the cavity contains, after the experiment, a Schrödinger cat. How can we probe it? Well, at the time we were not very, the experiments were not very developed. What we invented is to send through the box containing the Schrödinger cat a quantum mouse. And obviously a mouse that is in a superposition of alive and rotten is eaten differently by a cat that is in a superposition of dead and alive. And so at the end, the probability to get an alive mouse reveals a complex quantum interference process between the cat being dead and the mouse eatable, or the cat being alive and the mouse being not eatable. I'm sorry for this dirty analogy. Okay, it's very dirty indeed. But it works. This is basically the thing. I don't want to get into the details. That theory, you can look at it in the notes. But at the end of the day, we get a quantum signal which tells us how cattish is the cat in the cavity. If the signal is 0, it's at most a superposition, a statistical superposition. If the signal is non-zero, it's a cat. And what we observe is that we observed 96, it was a long time ago, is that we have a cat, indeed. But this cat doesn't live that long. This cat, this is, the unit here is the cavity damping time. This cat lives half or a quarter of the cavity damping time. And the only difference between these two curves is not the size of the current states, it's their separation in phase space, the angle between them. And then you learn something very interesting. You learn about decoherence. It's difficult to maintain for a long time a superposition of the cat's style. And the more distant the two states you plan to superpose are in phase space, the shorter the lifetime of the quantum superposition. So it's a major telling of the decoherence model is that quantum superpositions are of course feasible, but when you increase not very much the size of the system, but the separation of the states in a proper metric that you superpose, the lifetime of the superposition gets shorter and shorter. And that is one of the possible explanations why we never see in actual life a cat that is dead and alive at the same time. Why we are not at two positions at the same time, why a door is either open or closed and not both at the same time, and you can play metaphors in all the... Of course, this was a very crude experiment. Well, I will skip perhaps this lecture note. We tell you how to compute the decoherence of a cat and the decoherence time scale. It's just a simple exercise on entanglement. And it says that basically the decoherence time scale is the cavity damping time divided by the distance square between the two components in phase space. The distance square is homogeneous to photon number. So basically, it tells you that the damping time is the damping time of a cavity divided by the photon number difference between the two states. But of course, we made progresses, and more recently, we were able to reconstruct the Wigner function of the field inside the cavity. How do you reconstruct the Wigner function? It's called quantum state tomography. The key idea is take your system, make sure that you can reproduce its preparation as well as you can, and then make measurements on the system. Whatever you want. Any number of measurements, in whatever order you want, and resume, and make other measurements, not the same, whatever you want, and resume, and make other measurements. And at the end, use a beautiful algorithm that is called max-like, which provides you with a density matrix that is best compatible with the frequencies of the measurement that you have observed. So it's a very rich topic by itself. I don't want to come into details. There are hundreds of books and thousands of papers on quantum state reconstruction. But basically, this is what we did. We made measurements of the photon number distribution, because that we know how to do. We prepared a cat. We made measurements of the photon number distribution. But to make different measurements before measuring the photon number distribution, we would first translate the cavity state by some amount. And using 600 different translations, thousands of measurements for each translation, and 3 generations of students, and a large computer, we were able to reconstruct the field density matrix. And when you have a field density matrix, it's a trivial exercise to plot its Wigner function. And this is the Wigner function of a cat. This is 3.5 photon field dephased by 0.37 pi plus or minus. And you see the distinguishable things that I explained in my first lecture. The 2 ears of a cat and the moustaches or the smile of a cat in between that reveal that you have indeed a Schrödinger cat and not a mere statistical superposition. And of course, you know everything about that field. This is the even cat plus superposition. This is the odd cat. Nothing changes but the phase of the oscillation pattern in the center. I should make it fast enough so that you see the phase changing, and my computer will crash. This is the Wigner function of a statistical mixture. On purpose, we prepare a statistical mixture. We still have the ears, but we have no smile, no moustache. And the good news is that our Wigner function resolution measurement is resolved in time. So we can prepare a cat, let it evolve for a while, and then probe its Wigner function. And we can make a movie of a Wigner function as a function of time. And if the gods are with me, you will now see this movie. And what you see is that the fringes there get away far before the relaxation eventually merges the ears in the center of the cavity. In 30 milliseconds, this is a 130 millisecond lifetime cavity, in 30 milliseconds, the fringes are totally washed away, and you are left with a statistical mixture of the 2 cat components. Once more, I love it. So it's about 1,000th time slower than real time. So you see here decoherence at work. You see here that in a Schrödinger cat, the smile goes out first. And then long time after, the ears eventually drop and merge at the origin of phase space. This is a very important point about decoherence. Now I don't want, well, and you can of course measure that as a function of time, and you get a time damping of the coherence. That is precisely what you can compute. Everything works, quantum mechanics is right. There is nothing much new about that. But I think it's an interesting telling. Decoherence is now used somewhat in a fuzzy meaning where you speak of decoherence of a spin 1/2. In the original papers of Zurek, of Zé, and of many others, there were a clear distinction between 2 different times. There is the classical, so to speak, classical damping time. In our cavity is the lifetime of the energy, the photon number lifetime, the 0.13 seconds damping time of a cavity. But there is another time when it comes to mesoscopic objects. It's the lifetime of a coherence of a mesoscopic coherent state superposition. And this lifetime is definitely shorter than the classical damping time. And one way to recognize that you have a macroscopic or mesoscopic coherent superposition is that if you study it, you will find 2 very different time scales, that of a decoherence and that of a simple relaxation. And of course, for a spin 1/2, there is a factor 2 difference between T1 and T2, and there is no decoherence, stricto sensu. Okay. Is that clear? Clear enough? Okay? No questions? Ah, you seem to be dead. Well. Yes.
I have no question if there is specific remark. Maybe you have some hope and they're still in a superposition between a live and dead, not completely dead.
Yeah, there is one whose wave packet has been reduced on a live.
Do not make too many measurements.
So this one I can measure, I think. Yes.
So I'm not sure I understand correctly. Is there a way, without doing the Wigner function measurement, to tell whether no signal is actually a quantum state and not a problem in your lab?
It depends on what you are looking at. It depends on what you are looking at. If your no signal is a subtle interference phenomenon that disappears exactly as you prescribe it to disappear when you tune the parameters, you may believe in it. If your no signal is the total absence of fluorescence from the atoms in your vacuum cell, you might think that the laser is out of clock. The only thing to check that the signal is what you expect when it disappears is that it disappears exactly as it should as a function of the experimental parameters. That's the right way. So I skip tens of slides to show that the signal indeed disappears exactly as you can compute it. Okay, but and reappears if you turn back. That's another thing. It should go back. Okay. There is one good news and one bad news about fundamental quantum theory. The good news is that you know what you will observe. The bad news is that you exactly know what you will observe. So if you have surprises, is that the experiment failed. Okay, quantum feedback, I won't say a lot about that. I think I have 1/4 of an hour to go. It's a way of combating decoherence. Classical feedback, you know out of it. You all have an oven with a temperature regulation. Most of you have seen a car with a speed regulation. It's a system in which this is the old regulator of the steam engines, first feedback ever. You measure the state of the system. You have a controller that decides whether the system operates right at the setting point or not. And if not, it drives an actuator that takes a compensating action. Okay. And from this steam engine to your laser locks, there is absolutely no conceptual difference. What is quantum feedback? It's the same thing, but you have a quantum system on which you make quantum measurements. And the precise state is not a classical parameter. You want the system to be in one given state at any time. And to remain in that state, whatever happens. And of course, you have the same concepts, but there is a big problem, is that you need to measure to get information. That measurement changes the state of the system due to the projection postulate, and it makes quantum stabilization infinitely more difficult than classical stabilization. Imagine of a speed regulator on your car, which would randomly change its velocity each time it measures it. You would get sick very rapidly, of course, and it would be difficult to compensate. So we did that with one goal, which was to preserve a Fock state in a cavity. By the way, we have seen that in the chapter on relaxation. A Fock state leaves the time that is T cavity divided by n. By the way, it's the same time as a Schrödinger cat. And it's no mistake. A Schrödinger cat to decohere needs to lose a photon, basically. So it's the very same time. And so we made a feedback loop. We will get information on the cavity state. And for that, we use the less invasive measurement, which is a QED measurement of a photon number. Then we will have a computer in real time making complex density matrix calculations in tens of microseconds to decide what to do. And that's not trivial. Those computers are fast, but they are very, 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 very far from being real time. When you send an interrupt to Mac or to Windows, it can react in microseconds, but it can react in up to 1/10 of a second. So you cannot use it at real-time computer. And an actuator. And the actuator I would like to describe, we have made it with a classical current source, but the simplest is a quantum actuator. Basically, we will send an atom resonant with the cavity. In the upper state, if we have one photon less than what we expect. In the lower state, if we have one photon more, just to absorb it out. And in no state at all, don't send it, if the state is right. So this is the scheme of the experiment. We have a stream of atoms coming through the cavity. It's essential here to have fast atoms, because you want to extract a lot of information out of the cavity to maintain the Fock state, even if its decoherence time is only a fraction of a millisecond. So you need a huge feed of atoms. And we will detect them, estimate the state, and react on the settings, either to get additional measurements, or to send an emitting atom, or to send an absorbing atom. And here is the plot of what happens. This is the photon number probability deduced by the QED measurement, in shades with the average in black. These are the kind of atoms we use for the feedback. The others have no problem. We start with an empty cavity. The controller knows that. So he sends emitter atoms to feed the cavity. The efficiency of the emitter atoms is not 1, so you need to send many emitter atoms before you reach the prescribed state, which is 4. And during the sending of these emitter atoms, the measurement goes on. It's interleaved with QED measurement. So the controller thinks, oh, I'm at 4, I stop. So it stops, and we are at 4. And the controller keeps on measuring, so the probability to be at 4 even increases because we reinforce our confidence by gathering information that we indeed have 4 photons. But then suddenly you see that the controllers, the QED atoms tend to say, oh, there might be less than 4 in that cavity. So at some point, that triggers a threshold in the controller which say, oh, I should correct. Send an emitter atom. Well, it doesn't seem to work. Send another one. Well, it worked. I resume 4. Okay. And then you go on. And then it starts again. But then the controller is a bit overreactive. So it just sends too many emitter atoms. Or they have been too efficient. So most probably we jump at 5. So we'll send a couple of absorber atoms to compensate. And that goes on automatically forever and ever. And you can stabilize the Fock state like that just by controlling. This pleased very much the scientific writer of Le Monde journal, who wrote a beautiful piece where he compared this experiment to the level regulation in a water flush. We tried to coax him to use a less trivial comparison, but he found it neat, and the paper came out, a full page on that, comparing that to water flush. Sic transit gloria mundi, in Latin. So goes away the glory you can acquire in this world. Okay, I would like to devote 10 minutes to see you to say to you what we are working on now. A part of what we are working on now, and Leah will tell you what other experiments we are planning. I would like to speak a little bit of quantum simulation. Because in fact, perhaps the age of Rydberg atoms cavity QED is over. Just because everything we do, the circuit QED people can do. And there are very many. And so it's not clear that there is a bright future for Rydberg atoms cavity QED. But there is certainly a bright future for this idea, which is a quantum simulator based on Rydberg atoms, and that very much relates to the lectures that Antoine Brouwes will give next week. So he will tell you much more on that, and he has much more achievements that we have on that, but still it's exciting. So quantum simulation is just about this remark by Feynman, nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. Which shows that first, Feynman vocabulary was not absolutely academic, fucking shit, and which shows also that he got the intuition right. If you want to understand nature, either you have analytics, and you can make the beautiful things about Bogoliubov transform, and you understand anything. But not all systems can be understood like that. And for some, you really need to go to numerics. And numerics are doomed by the Hilbert space dimension problem. Imagine a chain of n spin 1/2. The dimension of Hilbert space is 2 to the n. Above n equals 42, and it's not by chance that it's 42, which is the answer to the big question, okay? Above n equals 42, it's out of reach of present-day computer. And even with more low, it will be 43 in 18 months, 44. You never reach the thermodynamics limit. So we have approximate methods, of course, DMRG, TDMRG, MPS. I don't know what they are. They just limit the size of Hilbert space by clever arguments. And they make it possible to go to 300, but they have limitation in precision, in the time they are valid, on the type of system they are valid. So if you want to really go deeper, follow Feynman principle. Simulate the quantum system, the chain spin, the spin array that you want to understand, by another quantum system. But not one that is found in nature, one that is man-made. One at which you can tune all the knobs of the interactions. One which you can measure everything. 3-body, 4-body correlations, n-body correlations, where you can measure everything. And then you will perhaps understand what occurs in the real system in nature, ITC superconductor, or anything like that. So you can do that analog. that is to build a system that has the same Hamiltonian. You can also do that digital. If you had a quantum computer, you could run the quantum computer to run the quantum simulation of any quantum system, because you can always slice any Hamiltonian in any other by an operation which is called Trotterization from Trotter. But I would like to go to analog quantum simulation. So analog quantum simulation, it's infinitely simpler than making a quantum computer. You just need high-quality individual quantum systems, interactions between them that you can tailor, systems to arrange them in 1D, 2D, 3D, and initialize them, read them out, and if you wish, introduce disorder, which is important for such phenomena as localization, many-body localization, and thermalization. So this looks within reach, and there are very, very, very many things that use quantum simulation with atomic lattices. I guess Hélène will tell you a lot about that. With trapped ions in 2Ds, with Rydberg atoms, Antoine will cover that. With superconducting circuits, there is a very active trend in Martini's Google team in Santa Barbara nowadays. Rydberg atoms are ideal for quantum simulation. Why? I leave it to Antoine to tell you why it is like that, but they have a large dipole, and since they have a large dipole, they have a huge van der Waals dipole-dipole interaction. Two atoms at 5 microns typically interact with a 10 megahertz energy. If you compare that to van der Waals in the ground state, it's 10 to the 11 larger. Well, it ranges like n to the 11, so there's a good chance that it should be. So Rydberg atoms are perfect, and once again, Antoine will tell you about that. He made beautiful experiments on two-dimensional Ising model. Lukin is making experiments on line on spins and phase transition in line on spins. It's a thriving, and it so to speak, revived the physics of Rydberg atoms in the last year. Rydberg atoms were very fashionable when I was, before my PhD, a master student, because it was very exciting to prepare them, make spectroscopy, and then it's a bit like AMO physics, they decayed away, and we have been for a long time with the late Herbert Walter, the only one to use Rydberg atoms in experiments, and then it revived with cold atom techniques and this idea of quantum simulation. But all the experiments so far suffer for limitations. They use laser-accessible Rydberg atoms, so short lifetime. There is the problem of atomic motion, but because of a strong interaction, the sample just explodes. The interaction is larger than any trap, and they are not trapped, in fact. And so the idea is, can we do better? And the idea is yes, with circular Rydberg atoms. Why that? I will skip rapidly through the slides, and I recommend you the publication with references somewhere if you need more info. First, Rydberg atoms have a long lifetime, 30 milliseconds. But you can make it even longer. Going back to Daniel Kleppner's idea, if you place a Rydberg atom between two parallel plates with a spacing that is less than half the radiated wavelength, at 0 temperature, your atom will live forever. Of course, if you want a finite size condenser, a finite conductivity, you won't get forever. But you can get up to 1 hour lifetime for a Rydberg atom with a realistic 2 millimeters per 13 millimeter capacitor. That's long, 1 hour, for that an excited atom. Well, of course, if you put in the finite temperature, if you put it, what will be the van der Waals interaction, we have further reduction, but 60 seconds, 1 minute lifetime is certainly reachable. That's long, 1 minute. It means that a 60 atom chain will live 1 second without being perturbed. Of course, if you want to use that, either you go to the outer space where there is no gravity, but okay, I'm not fit enough to go to the outer space, or you trap the atoms. The good news is that circular atoms can be laser trapped. That has been realized by Reitel a long time ago. Just because a free atom is basically a free electron. And a free electron has no transition. So any laser is blue detuned. So any laser puts an electron in a minimum of its intensity, expels it from the outer intensity. It's called the ponderomotive potential. And since a circular atom is nothing but a heavy rubidium ion loosely attached to the electron, If you keep the electron on site, the loosely charged ion will just follow. So you can trap circular atoms. Of course, that applies to any Rydberg atom. But the point is that the standard Rydberg atoms are very sensitive to something that is called photoionization. You absorb one photon from the trapping laser and you lose the electron. Circular atoms are not. They are exponentially not so. If you put a circular atom in 1 watt focalized to 1 micron laser, the lifetime is 10 to the 153 seconds. Okay. Take or leave a factor of 10 on the exponent. Okay. We are safe. And we did it. Yesterday. They did it. They trapped, and we see an oscillation frequency. It's not really trapped. But it's the first time we trap a circular atom for up to 10 milliseconds. We are not yet at minutes, but it's yet a progress. And it's better than what Antoine has achieved. Okay, don't tell him. Okay, so the idea we have in mind is basically trapping a chain of Rydberg atoms in a kind of 1D or 2D optical lattice, put them between the condenser plates, and let them interact through their interaction. And if you work out a little bit, 10 pages of computation, you get that the final interaction is this form. The sigma are the Pauli operators. So what do we recognize here? Sigma z times something. It's equivalent to magnetic field along z axis. Sigma x with something. It's a magnetic field along x axis. This thing, xx plus yy, is just the spin flip-flop. If you have one up, one down, you go to one down, one up, and back. Spin exchange. And this coefficient in our experiments is fixed, would be of the order of 17 kilohertz. And then we have an additional operation that is a ZZ operation. This Hamiltonian, in the parlance of spin models, is called the XXZ Hamiltonian. And it has plenty of phase transition. It has plenty of quantum phases. Well, plenty, a few of quantum phases. And the good news is that by tuning a microwave field that dresses the atom, we can tune delta and omega. And by tuning the electric and magnetic field that act on the atom, we can tune GZ. And we can tune GZ, delta, and omega all the way between many minus G's and many plus G's. And this is far enough to explore the phase diagram, for instance, that we would observe in delta equals 0, where you have paramagnetic phases, ferromagnetic phases, Néel ordering, all kinds of phase transitions. You see here DMRG projections of that. Of course, if you can compute that with DMRG, here with 90 atoms, it's not the ground state we will be interested in, but more dynamical phenomena. What happens if you go through this phase transition fast enough? What is the order? How much is it order? How many defects do you create? Kibble-Zorek mechanism. There is plenty of things on the dynamics of quenches in that system that are very, very hard to predict experimentally. So we have plenty of ideas, and we are trying to build it. But it's a long-term project. I will be dead before it's finished. But okay, it's fine. The young guys will go through it. Michel Brune will go through it with the young guys of the team. So I think it's important to point out at this stage, I'm finished now. It's important to point out that you cannot do science if you don't do a great teamwork. And one of the good things about the French system is that you can have senior people working out for a long time. I worked with Serge for 43 years this year. Yeah, 43 years. Well, now he's so much busy that we don't see much of him, but okay. With Michel for 30-something years. And it's important because it means that we can keep memory over a long time. Sébastien, Igor, and Clément join us more recently. So this is the PhD students and the postdoc who really do the job. And of course, you need money. And it's also important to realize that you need time. Science needs time. That was needs freedom and needs time. And I made a list of all the people who collaborated. We were in the team for more than 1 year. I don't think I have you, Philippe. You was Michel and Jean at the time. Okay, you should have added. So it started in 73 with Serge, who started the group coming back from his postdoc with Art Shallow. And it ended up with the last generation, Leah and Johan, who joined this year. Leah is there, so you can ask her how is it in the team. And you see many people, the violet ones are the ones who stayed in, and all the other ones you might recognize a few interesting names, Ephraim Steinberg, Paul Nussenzweg, Matthias Weidemüller, David Weiss, Veit Sandogda, who is now a big director at the Max Planck Institute, Peter de Mokosch, Ferdinand Schmidt-Kahler, some names which became famous in atomic physics. So you need time to gather such a team and to work with such a team. And of course, I owe many, many thanks to them. So thank you for your attention. I think I've finished now. If you have immediate questions before we get for a hearty lunch. No. Okay, so I have two things to say. I have a question for you and I have a remark. The first remark is that I will remain around most probably most of next week. Because I'm an emeritus, I don't teach, so I have plenty of time. This is a very, very fortunate position. There is a drawback. I'm old and I'm less paid than I used to be before being emeritus. Okay, never mind. Which means that I have to rely on invitation to take vacation. So that's the first remark. So whatever questions you have, we have plenty of time to discuss that. Another thing is that being a scientist is not now my only occupation. I am also the lead editor of Physical Review X, which is one of the key publications of the APS publication system. I understand that you are all at the beginning of your PhDs and will soon write or are writing your first papers. If you would like to get an introduction to the publication system and to the APS publication, we could arrange next week at the time of heavy rain, I don't know, 1 hour meeting, 1 hour expose and discussion, 30 minutes me speaking and perhaps 30 minutes of discussion about what are publications, how do I get published, how do I cope with fierce, savage editors, how do I cope with these fucking assault referees, sorry for the vocabulary. So if you wish, who would be interested? Okay, set the debate, I think. So we will tell you, we look at the weather forecast because I don't want to interfere with you hiking, but we will set that up for next week. Thank you.